So yeah, my name is Zach, and today I'll be presenting my project, which is the porting and performance tuning of SeisSol on multiple HPC architectures. So as we know, HPC systems have over the last, well, really 50 years have increased in performance significantly, and with the latest systems now able to exceed 1 exaflop. So with that, simulations have been able to, be larger simulations be conducted, with more accuracy as well. But with that additional computational power, systems have become increasingly complex across the board, from hardware, CPUs, GPUs, accelerators, all the way up to software. You have different compilers, how memory is laid out, NUMA topology. So it makes achieving performance portability for software increasingly challenging. And so as I competed in the student cluster competition, I kind of extended that and investigated the performance of an application across 3 different HPC systems, and what optimizations and tuning strategies can be applied, and that can inform us of basically tuning strategies for SeisSol. So I'll show you. So here are the 3 different systems that I investigated, which is Bridges 2, Archer 2, and then a TeamEPCC cluster. 2 of these are CPU-based that share the same type of CPU. And then the final one is a H100. So what exactly is SeisSol? SeisSol is an earthquake simulator. It is used to simulate seismic waves and earthquake physics. For example, on the right, you can see that here's a hypothetical simulation of an earthquake in northern Iceland, which was used to study the tsunami impacts on coastal towns. And it's using seismic hazard assessment, academic research, as well as oil and gas exploration. It is a hybrid parallel application, which utilizes both MPI and OpenMP, or CUDA if it's on the GPU. And one of the 2 key features of SeisSol is its ability for kernel code generation at compile time that can automatically convert the numerical scheme into efficient matrix multiplications. But the second is that it uses 2 types of communication modes for MPI, either polling or threaded, which are investigated as well. So quick overview of what the competition is, which I originally competed in, and on the TeamEPCC, where my task was to achieve the best performance on 4 CPU nodes of Bridges 2, and compare what the polling differences in performance between polling and threaded, to identify the 3 most top MPI cores, and to produce a video of a simulation. And the actual benchmark that I was investigating was the Turkey benchmark, which is an earthquake happened in 2023. So firstly, Bridges 2. So one of the first things I did was investigated. So SeisSol has 3 types, also has 3, I should say 2 types of benchmarks that I initially used before the larger one, which is a proxy application, which is a small single node tool, which I used to, first of all, check all the kernels worked correctly, and also to evaluate the idealized single node performance of just the kernels. So I selected GCC and the PSPAM code generators, and it gave me about 675 gigaflops initially. So kind of gave us an estimate, indicated that at 4 nodes, we should be expecting around 2.7 to 3 teraflops. So I investigated the NUMA effects, the non-uniform memory accesses, across. So on Bridges 2, there are two NUMA regions, 1 per socket. And so that kind of aligned with the initial performances of allocating 2 MPI ranks per node and 64 threads each. So based on that, I selected that option going forward. I conducted scaling up to 1 to 4 nodes, testing the 2 different communication modes, polling and threaded, as well as the different OpenMP placement strategies, where I found that at 4 nodes, polling with a spread allocation achieved the best result at 3.2 teraflops. And so through our investigations as a team, we also found that the base OpenMPI implementation was not as efficient as we would like. And so we included outdated dependencies, and also critically did not include UCC. So what we did, we built our own version of OpenMPI with a more recent version of it, as well as include UCC, as well as those 3 compiler flags that you see there to make sure that we generate the most efficient instructions for the Zen 2 architecture. And by doing so, we increased the performance at 3 nodes by 180 gigaflops, and also at 4 nodes by 300. So by the end of the competition, I was able to achieve 3.62 teraflops, simulating the Turkey benchmark by just under 18 minutes. Now, the other two tasks which I did was using Scalaska, I identified those MPI functions as the most frequently used. Critically, during the simulations, MPI test and start. Test is used to progress the communication engine, and then start for the persistent communication that it uses. And finally, as you can see here, this is the Narali fault and the East Tertullian fault, and you can see how the earthquake propagates there and then hits from the surface. Now, on bridges 2, it's quite due to the competition restrictions where I was only able to go up to 4 nodes. It was, I couldn't see the full scalability of SeisSol. So using Archer 2, I was able to extend that to up to 128 nodes and see if what I could kind of investigate there. Again, using the proxy application, using the 3 different programming environments, I found that well, the highest performance I achieved was with the Cray compiler using the libxmm. But to ensure, I had issues previously on bridges 2 with libxmm. So what I did on Archer 2, I selected libxmm because it's tailored for the AVX2 instruction sets, which Zen 2 uses. And to ensure consistency with bridges 2, I selected GCC. And we can see as we go beyond 65,000, it decreases due to likely due to the lower level caches exceeding. So unlike bridges 2, although they share the same CPU, Archer 2 uses 8 nodes, regions per node. And I could see that based on my results where I found that 32.4, 16.8, and 18.16 outperformed the other configurations. But what I found that there wasn't at one particular node count, one didn't significantly outperform the others. So using those 3 configurations, I extended that to a full scale 1 to 128 nodes, where I found a significant difference between the polling and threaded communication modes. And the reason why I found there was a difference is that I found that in order to use threaded, each MPI rank needs to allocate 1 core. But due to the strong minimum effects on Archer 2, more cores need to be reserved. And so you lose more cores from the computation for communication. And so let's say at 16 MPIs, it's about 12% loss of cores, whereas at 32, it's 25%. And that's why you see the greater number of MPI used, the lower performance you had with threaded. So that's why I selected polling, and I found that 16.8 was the most efficient at 64 nodes. But through my investigations, I found that initialization was actually a key bottleneck for SeisSol, where that's at 64 nodes, 50% of the runtime was now initialization. And this was ultimately, and I found that the greater number of MPIs used, the longer that initialization would take, indicating something to do with MPI. And I found through Cray profiling that collective communication, specifically all-to-all V, there's an issue with its implementation in the current default communication layer on Archer 2. And this was also consistent with previous work. They also found that in other applications. So I investigated. So by default, OFI establishes connections between MPI ranks lazily, meaning that when they first want to send a communication with each other. But since SeisSol distributes the mesh straight, using all-to-all V at initialization, that was the cause for the slowdown. And so what I did instead was enabled eager connection, so it establishes connection straight away at initialization. And also I investigated UCX, an alternative communication layer, to see whether that's just an OFI issue. And I found that for both of them, I was able to reduce the collective time by about 97 to 99%, from about 15 seconds down to a few milliseconds. And the UCX showed the most improvement in the initialization time by 82%. So what does that mean in terms of full runtime? This on the left is the original parallel efficiency, and this red line here is the actual gray line here. And you can see through my tunings, I was able to increase the parallel efficiency. And so what's important to note that performance is not the most important sometimes. Efficiency, if you are a SeisSol developer who wants to reduce your resource usage, I believe that 16 nodes is the most efficient. But obviously that increases time to solution, whereas if time to solution is more important, that I believe that 64 nodes is balances the two. And for example, let's say you wanted to run the big benchmark on 64 nodes 100 times. If you were to just run SeisSol by default, it would take about 185 CUs, but through my tuning, it reduces to about 116. And then the final, so SeisSol recently added support for GPUs. So I wanted to evaluate its performance on the TeamEPCC cluster, which has 16 H100s. Using the proxy application, which is again single GPU, it has 3 types of kernel generator, sorry, 2 with additional support for CUDA graphs. The original implementation had many different kernels, but through optimizations, they chain forge, obviously the word chain, changed them to get into a single kernel, which reduces kernel launch overheads, and that's what kind of validating the performance of previous work, because they haven't looked into H100. So their most recent one was A100, and I showed that I was able to achieve about 1.44 teraflops greater performance compared to the A100. I did, again, strong scaling with the Turkey benchmark, but unlike on Archer 2, where due to the strong NUMA effects, threaded communication now outperformed polling, reaching about 33 teraflops on 16 GPUs. But interestingly, once I'd gone from 8 nodes to 16 nodes, I saw a large performance variability. So at some runs, I would achieve about 19 teraflops, and other runs will be 33. So it was about 15 teraflop difference. And through my investigation, I ultimately concluded that HPCX, the default communication library by NVIDIA, was inefficient, especially 23.9. And on the left, you can see that kind of performance variability and the 2 nodes where I would so when I'm launching the application, I could either choose to launch from node 1 or node 2, but at the same time, I'm always using both nodes. Because I thought that initially there was some I noticed the performance difference on the second node. But ultimately, I found that this was not the case. It's just always high performance variability. And by upgrading the HPCX version, I was able to reduce that variability by about 10%. And in doing so, I increased the average performance to about 27 teraflops. So overall, I would say my project was largely achieved the main goals I set out to achieve. Testing SeisSol application on 3 different HPC systems, I found that for architectures that have lots of NUMA nodes, it's more advised to use the polling communication mode instead. And this is actually consistent with previous work. And so by extending my evaluation to these systems, which have just yet been unexplored, I can kind of contribute by showing the performance of additional systems. So the one thing that, due to limited time, I would like to do in the future as well, is to first evaluate the OFI backend on Archer 2, whether this initialization bottleneck is simply due to the fact that it's an old version, and whether the newer versions of OFI still have this bottleneck. Also, I would like to investigate why exactly HPCX was causing that performance variability, because yes, I did solve it, but if I could actually investigate the root cause as to why it was causing that, I could potentially, maybe that's implementation, something I could change. And also, again, additional systems that I could benchmark SeisSol on. And yeah, thank you very much. So.
I have another question. One question. Okay, so for the Archer section, I think you showed this kind of saturation picture with performance against cells or something.
Yeah, so the simulation.
Can we just against cells? I think you were calling it.
Oh, on Archer 2. Okay. Yeah, this one.
Yeah, this one.
Yes.
So I assume I interpret this as problem size.
Yeah. So
okay. Yeah. So what's happening? What did you say is happening?
So the proxy application is, since SeisSol is a large application, they provide a small tool called the proxy, which is just, it excludes initialization or I/O. It's simply just performing the computational kernels. And so you can select how big your problem size is. And so what happens, basically what we see is, it increases, but the reason why it drops, which I believe, which is like, I didn't investigate specifically the proxy because that was not my goal. It was the scaling, but the likely reason is because by increasing the problem size, it exceeds the lower level caches. And then there's increased memory latency because it has to, and so, interestingly, you'll notice that the best performance is between 32,000 and 65,000. Well, the original Turkey benchmark has about just over 2 million. So if you do 2 million divided by 64, it's with about 35,000. So it kind of confirms that at 64 nodes, that's why we expect the best performance. It kind of aligns with my expectations.
Thanks. So when you were talking about the problems with initialization and that all-to-all V,
yeah.
So did you consider how, if you were going to advise your developers of the application, what they might do, did you consider how the all-to-all V might be replaced with other communication patterns? Because I think people who've been doing this for a while know that every time you've got an all-to-all, you potentially have a performance problem. And I mean, it may be that developers go, oh, we only run it once at the start, it's fine. But you've clearly shown some evidence that this is a problem, at least in some MPI library settings. So would you have any advice for them on how they might change their communication pattern from looking at the code?
I guess if you wanted to avoid all V, you can just do point to point, I guess, but it's not as efficient. Whether I think, because the previous works have also, they use all-to-all V and they show that it is actually efficient. It's just that the fact that it's running on Archer2 is the reason why it was inefficient. So there's something with the 1.12 on Archer2 that is causing that inefficiency within the implementation.
So it's Archer that's the problem?
Yes. Yes.
Okay, thank you.
Yeah, thank you very much.
Somebody wrote a question.
Shall I read it? On difference accuracy, why would different hardware affect that?
Could you read the question aloud?
Yeah.
Oh, sorry.
It's the standard.
I don't know if
The
that's,
second one.
is that previous one?
For TeamEPCC cluster, it's that one. Okay. For TeamEPCC cluster, the use of threading communications is better. Is that due to the communications in GPU to GPU, or is the communication still CPU to CPU?
No, the communication is, so you can, through an environment variable, you can change the communication mode. Either you can have it direct, GPU, or host, which goes back to CPU. But I think the main reason why is just simply the loss of cores, which was the difference between polling and threaded. And since the computation now happens on the GPU, there's no loss of cores or any NUMA effects. So,
Yeah. Perfect. Yes. Follow.
Thank you. Okay.
oh, okay.
That's it. Thank you.
Yeah,
That's all.
okay.